you started.
Hi, thank you for coming. We are Team Bandana Slugs. I am Erin Rowan.
I'm Mark Steinke,
Hugo Romero. I'm Nick Gustin.
and we will be presenting on our design ElectroLock, a bike security system.
So this is our quad chart, explaining our objective, concept, approach, and schedule and cost. So our objective is to make bikes, specifically on university campuses, safer. A study shows that about 29% of bikes get stolen from these campuses. SPU is excluded from that, but that's only because we're a really small school. So our concept is that we will create an easy-to-use bike locking system that is controlled by RFID. So an RFID card is like your CPAC pass, or like a UW card, or like a Metro pass, I think. So we'll have an alarm system in it, and basically what you'll be able to do, our approach is a user will be able to go up to the bike lock, scan their card, and then lock up their bike. And then later, when they need their bike again, they scan their card, and since the system has recorded their ID number or card number, only they can access their bike. The security system is there so that in case the lock gets cut, which we will do our best to prevent, an alarm system will happen. And it'll be loud. We were thinking of maybe having some sort of notification system for you or for like safety and security, but that's not really our main goal. And so yeah, that really just increases the safety of your bike. And then for schedule and cost, our key milestones are initial prototype by December, revised prototype by February, field trials in March, April, and then our final design by late May, early June. Our costs, we're hoping to keep under about $600 for our materials. We're going to be using high-strength steel and high-quality electronics. So we're going to try to keep those costs down without compromising the integrity of our system. And then our labor hours, we estimate to be about 1,440 total person hours between the four of us. And for an engineering salary of about $40 an hour, that puts us at $57,600 for our budget.
So the problem space that we're trying to tackle is mainly bike theft, where it's the #1 crime across universities. Statistics from the Seattle Police Department from last year claimed that more than 1,500 bikes last year were reported, or 2015 were reported stolen, and that translates to about 4 a day. And in the past 8 years, bike theft has gone up by more than 16%, which is roughly an 18% increase every year. And these statistics here are just the reported bike thefts. So the actual numbers are a lot higher. And then another study in 2010 from the University of California, Davis, they claim that about roughly 3,000 to 3,500 bikes were stolen from the 1,300 campuses there. Meaning there's a 29% chance that a student's bike will be stolen during their first year of attendance.
So here we have the block diagram of our system. I'm going to go ahead and start by explaining the more electrical aspect of the block diagram, and Erin will come and explain the mechanical aspect, because they are very integrated, however also separate. So as you can see here in the block diagram, we have the center of it all will be our microcontroller unit, which we will be using a PSOC 4 device for this. For the current prototype that we're using, we're going to use the Pioneer board, which just has a little bit of everything encompassed in it, because we believe that will be easiest to use and what we already have experience with. We will have that connected to a motor control shield, which is just essentially a device that's used to help control the motors and give them power when we need them to have power, as well as control them, especially if they're a stepper motor or whatnot. We'll be able to communicate with the motor through the motor control shield. The microcontroller unit will also be connected to an RF reader, which will help us connect with a tag and read a tag whenever the tag comes within the required distance of the reader, it will scan it and transmit that data to the microcontroller. Also, we will have a number pad and an LCD screen associated with the device as well, so that way the user can choose which station in the bike, which bike station they want to be using to lock the bike into, and then we will be able to communicate correspondingly with that bike station. And then there will also be a database that we will contain all the records of people who have locked and unlocked their bikes at that station and at what time, just so that way we can have that information for resources of doing research in student habits, as well as if there happens to be a security breach, which there won't be, we can go back and check the records. Also highlighted in green here is the critical path aspects of the design. So I'm going to go ahead and explain the critical path aspects of the electrical side. And that will be mostly associated with the RFID system and how that will be communicating with the RFID, with the microcontroller. And so this is one of the aspects that Hugo and I have the least experience with, which is why we want to make sure that we're diving into and making sure that we can get this aspect working. This includes sending the tag data through the reader to the microcontroller, as well as just communication and power of both those devices. We also will want to have the motor control shield working for the locking mechanism, because in order for the mechanical aspects to be working, we need those motors to be operating effectively, so that way they can test their aspect of the design. One other thing that I forgot to mention about this is that we also will be supplying with wall power, which will be stepping down with an AC to DC converter, so that way we're getting enough power. However, we might consider using a battery or other sun system to store extra energy in case wall power is lost.
Okay, so now I'm going to cover the mechanical aspects of the block diagram. So everything mechanical is in blue. So essentially, if you look over here to the right, this is your U-lock. This is the big bar that comes out that you actually secure your bike with. So U-lock comes in and it goes into these two lock chambers. And the way the lock chambers work is you've got two motors over here that will have two gears on top of each motor. So as it turns, we'll have a way to transfer that power into mechanical power. So the motor gear connects to a gear train. So we're going to be using a rack and pinion system, which is illustrated here. The rack and pinion system takes rotational power and turns it into linear power. So that's what's happening here. You've got the piston, or the pinion, and the rack, which then on the rack will be a bolt system. So a series of maybe 3 or 4 bolts that will be moved into the lock chamber on both sides. The U-lock is going to have holes in it for the bolts to slide through. It's going to act a lot like a deadbolt on a front door. And then, sort of just as a side note, once those are locked, we'll have the security system in place there, so it will emit current through the U-lock, and then if that current's ever broken, that's what triggers the alarm. So, also highlighted in green was our critical path. So for us, it's designing the actual locking mechanism, making sure our rack and pinion system works. We have to make sure that it will completely lock, and it won't be able to be back driven, so turning the motors backwards to pull the bolts out. So we have to make sure that won't happen so that the lock can't be broken into through a more intelligent way. So we also are going to have to make sure that the gear ratios are correct for the power of the motors. So we're going to have to make sure the power coming here will be enough to both move the rack and move it enough. So distance and sort of, I guess, time for that. Additionally, we have to make sure that the motors will respond to the motor control. We have to make sure that everything will be able to be integrated both from mechanical and electrical, because both are pretty much dependent on each other for the whole system to work.
For our Q1 specs, we are saying that our locking system shall implement a RFID technology as a means to unlock and lock our system. So for this to work, the tag needs to be within 3 inches of the reader. And we chose 3 inches so that the user would literally have to just place the card right in front of the reader, and this will be countermeasures for any false positives or false negatives. In addition, we also want the system to be very reliable. So the system should be able to unlock and lock the bike rack 100% of the time. Our second spec is the locking system shall be able to lock and unlock in a timely manner. Meaning, we don't want to compromise the length the user has to take to securely lock the device. So we want to make sure that the system does not take more than 15 seconds to unlock and unlock the system. We're shooting for 5 seconds.
As for the more mechanical side, the lock is going to be highly resistant to break-in, so we're going to make sure that it can withstand the pressure of about 300 psi. One of the most common ways that more of your high-class criminals steal your bike is they use a mini hydraulic lift, and they sort of insert it between the bars, and it expands out, and it just breaks right through your lock. So we're going to try to create a lock that's strong enough to withstand that. And then it'll also withstand a temperature of about 1,000 degrees Fahrenheit. The melting point of your typical steel is about 1,500 degrees Fahrenheit. So we're going to shoot for a high grade of steel that can't be melted off. And additionally, the force will try to keep to withstanding about 5,000 newtons, which is roughly the weight of a horse, which translates to somebody can't just yank it off. It'll withstand most methods to steal your bike.
For engineering analysis, on the electrical side, one of the main things that we're going to look into is the power consumption of our device as a whole. This includes the motors, as well as the microcontroller, the reader, and the motor control shield, the sensors, and all of that together. And so this will have actually 2 aspects, one being the active power consumption, which is when the device is in use, being used by users who are locking and unlocking their bikes, how much power in watts will it be requiring, and then also the sleep state power consumption, which will be when it's not being used and inactive. And so between these 2 numbers and estimating the approximate estimated active time and sleep time, we'll be able to calculate how much power this device will be using over the course of the day or longer, so that we can know if there is a battery, how long that battery life would last. Also, we're going to want to analyze the RFID reader distance and make sure that it is a very close proximity sensor, which is why we plan on using NFC, which for those of you who don't know what that stands for, it's Near Field Communication Device, which is a subset of RFID, which RFID, for the record, is radio frequency identification. And so through that, we will be able to, we're going to analyze how close the card has to be to the reader, as well as the frequency that the reader and tag will be operating at. We're also going to want to analyze our locking sensor accuracy, and this will be the sensor that's keeping track of where the lock is moving in that bolt system, so that way the lock doesn't overextend, or the motor doesn't overextend, or not fully lock. And so that way it will ensure that the lock is always fully and properly in location. And then also there's going to be the storage capacity, and this is going to be something that we will be able to likely choose ourselves, but this is important in knowing how many records of data we'll be able to store of when and which people unlocked and locked their bikes at what time.
So on the mechanical side of our analyses, we'll be doing structural analyses. So we're going to run an FEA on the bar itself, and also the bolts to decide exactly how much force these elements will be able to take before they break. We'll also be analyzing the power that the motor will need to open and close the locks. And we're going to analyze decide the tooth relationship between the rack and pinion to know exactly how they're going to fit together and how many teeth the gear on the motor is going to have. Then we're going to have to find out exactly the linear distance to motor turns ratio so that we know how many turns of the motor it will take to open and close the lock. And here's our schedule. In red is our critical paths. Right here is our mechanical critical path. And here is our electrical critical path. And so these are the most important things that we're going to be trying to achieve in this quarter. In mechanical, it starts with creating a CAD model of the lock design, and then choosing the material of the lock, and then 3D printing the lock, and assembling, testing, prototyping the lock system. And then for electrical, it'll be, we've already chosen PSOC as the microcontroller, and then we're also going to have to order the RFID, the reader, and the microcontroller, and then figure out how to put them together, how to connect them so that they will work together. And there'll be assembly and testing, and then prototyping at the end of the quarter. All ending with our design review here at the end of November.
So for our critical path device, our RFID system, all components will be bought. So that includes the RFID tag, the RFID reader, and the PSOC or microcontroller. And the way this system is going to work is as follows. The reader is going to continuously transmit a signal, and when RFID tag is within proximity of the reader, it will power up the reader, and as a result, the RFID tag will send a signal back to the reader, forming a two-way communication. Once the reader receives the information from the tag, the information will then be spit out to the PSOC or microcontroller. And from the microcontroller, the data would be processed through a database, and from there it will activate the motor control, and then will follow with the unlocking and locking of the locking mechanism.
As for the critical device for the mechanical aspect, we are going to be showing the locking mechanism. So eventually we will be using high-strength steel, but for the sake of time, we're going to be 3D printing most of our materials. Metal takes a really long time to machine, especially if we're going for extreme accuracy and strength. So 3D printing really just saves a lot of time and a lot of money for a fall quarter. We're going to use pre-manufactured gears, though. We're not going to 3D print them. So 3D printing is sometimes really inaccurate due to the shrinkage of plastic and CAD models that don't work. So we're going to use pre-manufactured gears so that we make sure our rack and pinion system is working. So essentially what we'll be building is the locking here and the locking here, where the locks will slide into the bar when it's inserted. So our goal is to go for one motor. We've sort of planned for two just in case, but here, as you can see, we're hoping for one because the rotational energy would push this lock over to the left, and then it would translate down and push it over the other one over to the right. So that's our goal. And additionally, we have this locking cable. So the bar will be able to be pulled out, because this will be on sort of like a wrapped up thing, sort of like a hairdryer. And so when you take it out, it won't be able to be stolen for whatever reason. Someone would want to steal that. And yeah, so this will be our design, and we'll do our best to get it done. Are there any questions?
20 minutes on the dot.
Nailed it.
Oh, I didn't save it. My bad. Oh, it didn't stop it. My bad.
No.